Hey guys, in this video we're going to look at lesson 6.2a or 6.2 part 1. We're going to discuss confidence intervals for the mean with small samples. Just to look back, 6.1 was all about creating these things called confidence intervals for the mean with large samples. And specifically, we were dealing with large samples in which we knew the standard deviation, at least speaking for the first part of that lesson. So the situation in 6.2 gets a little more applicable to real world situations. So for those of you that may go on to use statistics in your career path, in your future job, this is closer to reality. In many life situations, the population standard deviation just isn't known. It's too hard to gather information from the entire population, and even more so because of various constraints such as time and cost. It's often not practical to collect samples of size 30 or more. That's even too hard to do. So the question is, how can you construct a confidence interval for a population mean given such a circumstance where you have a small sample size of less than 30 and you don't know the population standard deviation? If the random variable is normally distributed or approximately normally distributed, you can use something called a t-distribution. We've been using z-distributions. We're going to look at something called a t-distribution in this lesson. So our aim here is to be able to figure out the critical value for t. It's noted t sub z, or t sub c rather. So that's our first example, and then our second example we'll actually build an interval, a confidence interval, using a t-distribution. So first, what the heck is a t-distribution? So the situation goes, what if we do not know the population standard deviation and we have a small sample size? If the distribution of x is approximately normal, and that's the key part here, it needs to be approximately normal, we can use a t-distribution instead of a z-distribution. So facts to consider. First, the t-distribution, just like the z-distribution, is bell-shaped and symmetrical about the mean. The t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. So it's a family of normal-looking curves based on degrees of freedom. So this is a term specific to this topic. It's a vocab term, degrees of freedom. What is a degree of freedom? Well, it's simply one less than whatever the sample size is. So if you have a sample size of 20, let's say, your degrees of freedom is 19. The key idea with the degrees of freedom is it's measuring how close to the true normal curve, okay, the true normal curve, our small sample is. The smaller the degrees of freedom, meaning the smaller the sample is, the further from the normal curve it will be. Okay. Under the area under the t-curve is 1 or 100%, just like the z-curve or the normal curve, and the mean of t-distribution has a t-score of 0, just like how the mean of a normal distribution of a z-score is 0 as well. So it's going to behave very similar. You can see here a very blurry image here, but I want to highlight a couple things. The first of which, our normal distribution, our normal curve gets lower, and then in the peak, it peaks higher. So here in green is our normal curve. Normal. Okay, that's our standard normal curve. All right, and then just so we have an understanding of how this changes, if we have a a degree of freedom that's, let's say, oh, I don't know, I'll highlight the one that's next closest to it. So it's a little higher on the tails, but then lower in the middle. There. And then we're just barely higher there. Okay, that would be a curve with a degrees of freedom of pretty close to the real normal curve. Remember, 30 is our sweet spot, 30 and above. So maybe this is like 20, let's say, just for the sake of example. And then, you know, if we go even further from this, so you can see that curve peaks much lower. The tails are fatter, yet we would estimate the degrees of freedom for this curve to be maybe somewhere around 10, maybe a little bit less. You know, by just looking at them, you would never be able to know what the degrees of freedom are. The point of this is to show how the graph changes compared to the green normal curve, which is our standard that we've been operating with. So the smaller the sample size, the shorter the graph is going to get, and the fatter the tails are going to get. Okay, so example. We're going to find the critical value t sub z for a 95% confidence interval for a sample size of 18. Okay, so the first thing we need to do here is figure out what our degrees of freedom are, because remember, these critical values for our t-scores are based on the degrees of freedom. So remember, our degrees of freedom are the sample size minus 1. In this case, our sample size is 18, and 18 minus 1 is 17. Awesome. Okay, so now we want to figure out what our z sub c value is, our t-score value for a confidence interval of 17. So I'll switch to red. What is the t-score for a 95% confidence interval with a degree of freedom equal to 17? How would we do this? We're going to use our t-chart. So a t-chart has been provided for you. I'm going to go ahead and jump to mine. All right, so t-chart, pretty simple to use. On the top here, we have our level of confidence. We were told that we are operating at a 95% confidence level. So I'm looking in this column here. So I'll just continue looking down in this column here. And then I have a degrees of freedom of, I believe it was 17. I'll change it if it wasn't, but assuming I'm right, so we have 17 right here. So my t-score would be 2.110. Let's just make sure I'm remembering the right number. Yes, I am. Awesome. All right. All right, 2.110 would be my t-score. So that is an example of finding a t-score. At this point, we may not understand where we're going with this information, but we're starting somewhere and we're going to build on this. And we just need to start with finding these values. Then we'll build from there, okay? All right, last example. You randomly select 16 coffee shops. Fantastic. And measure what are we saying here? You randomly select 16 coffee shops. I believe what it's supposed to say here is you randomly select, hold on a moment. You randomly select 16 coffee shops and measure the temperature of the coffee sold at each shop. That's what it should say. So we have 16 coffee shops, our N value is 16. The sample mean temperature, is 162.0 degrees Fahrenheit with a sample standard deviation of 10.0. Okay, so that's nice that they tell us our sample standard deviation is 10.0. Perfect. All right, find a 95% confidence interval. Good, we know our level of confidence is 0.95. For the mean temperature. Perfect, so they give us a whole bunch of information here, so we can go ahead and figure this out. So because the sample size is less than 30, sigma is unknown. So yeah, we have our sample standard deviation, but we don't have our population standard deviation. We're not sure what that is. And the temperatures are approximately normally distributed. So we can use our T distribution. So these are the building blocks of T distribution. And I'll just mention these here. So 1, sigma is unknown, and 2, n is less than 30. So we use our T distribution, which is what this lesson is all about. I apologize, that got a little scribbly there. Okay, fantastic. So we have all of our information listed here. The next thing we can find here would be our degrees of freedom. Now that we've decided we're going to go the route of using a T distribution, the first thing we want to do is figure out the degrees of freedom. So it would be 16, which is n less 1, so 15. Perfect. After that, we're going to want to find our T-score, our critical value, using that chart. So we have degrees of freedom of 15 and a 95% confidence interval. So I'll jump to my chart. Let's see here. So degrees of freedom are 15 in this case, and 95% confidence interval, so it looks like 2.131 is what we're looking for here. So two 2.131. All right, now the process is going to resemble very closely the process we used in 6.1. All right, so we're going to start by figuring out what our margin of error is, because remember, here's where we're operating. We know that we have a sample mean of 162. We're trying to build a 95% confidence interval for that. So in order to figure out what my margin of error is, I will use that formula. The difference here is we're using T sub C instead of Z sub C. So that is the only difference here in this formula. And then we have our sample standard deviation, so we'll use lowercase s for that. I've been using sigma sub x bar in my class, so those are both fair ways to say that. I'll circle that just in case you missed me writing that over the square root of n. So same formula or same essential building blocks. So here we have 2.131. Let's make sure we get that right. Times, we have a sample standard deviation of 10 divided by the square root of 16. And when we punch that in, we get approximately 5.3. Okay, perfect. So my confidence interval would be 162 plus 5.3 to get the high side, so 167.3, and 162 minus 5.3 we're looking at roughly 156.7, yeah, 156.7 degrees. So that means that my interval, my confidence interval is 156.7 all the way to 167.3, just like that. Perfect. And this again means that I'm 95% confident. So we can say with 95% confidence, we can say that the mean temp of coffee sold between 156.7 and 167.3 degrees. Is keyword there. So with 95% confidence, we can say that the mean temp of coffee sold is between those two marks. And when we say the mean temp, we mean the population mean, because that is what we are providing an interval range to estimate the location of with 95% confidence. So very similar in practice to what we've been working on in 6.1. The added difference here is, again, back to the red blurb right here on the left side. If we don't know the population standard deviation and we have a sample size of less than 30, we need to go this route. Thanks for watching, and as always, let us know if you have any questions.